Hi everyone. In this lecture, I'll introduce some terms which we'll be later using in noise figure and sensitivity analysis of RF circuits. So one of the common terms is available power. So let's say I said that most of the RF amplifiers or antennas can be modeled as a voltage source and a resistance in series with it. So antenna, we already said that the losses in an antenna can be modeled as a resistance and the input signal can be modeled as a voltage source. Similarly, if, for example, say you have cascaded two amplifiers, call it A1 and A2, then the amplifier as seen by A2, this entire part can be modeled by a Thevenin equivalent and an equivalent resistance. Okay, so this comes from basic circuit theory concepts, so we are aware of this. Now, what we are interested in finding in this lecture is the available power, so which is the maximum power that a voltage source of value Vs and a source resistance Rs can deliver to a load resistance RL. Now we know from basic circuit theory concept that when your RL equals Rs, it's called the matched load condition. At that point, maximum power is transferred to the load resistance. So when RL equals Rs, the voltage appearing across the load resistance is Vs by 2. So that whole square divided by RL will give me the maximum power that is delivered to a matched load. So it will be Vs square by 4RL or it will be Vs square by 4Rs. So this is a property of the source itself. Okay, so Rs is again a property of the source and Vs is the input source, input voltage source. So this will be the maximum power that a source of voltage Vs with the source resistance Rs can deliver. So any power, when you connect any load of value RL, it's always going to be less than or equal to this number. So this term is called the available power or available source power. Okay, so Vs square by 4Rs is called the available source power and units are in watts. You can also express it in dBm. In a similar fashion, we will also discuss a term called available noise power. Now, what is available noise power is that, say we have a source resistance of a value Rs. Now we know that we can model noise as a voltage source in series with the source resistance of value, say Vn. Now we know Vn square, the spectral density of the noise, is given by 4 kT Rs. This is the one-sided spectral density. So for this is what is 4 kT Rs? It's the thermal noise, the noise voltage developed across the resistor, or uh, it's the thermal noise. It's because of the random thermal agitation of the electrons in the resistor. Okay, so if the temperature is 0, there is no noise. That's what this equation is telling us. So this is the spectral density. If we take the power spectral density, okay, then this spectrum is called two-sided spectrum, which exists for both negative and positive frequencies. For a resistor of value Rs, it is 2 kT Rs, and I can also represent it as a one-sided spectral density. So I have to deal with only positive frequencies in all my mathematical calculations. So that's written as 4 kT Rs. So this is called the one-sided spectral density. Now, because you can actually model the noise as a voltage source in series with the resistance, what happens if I connect a load resistance RL? The question is, can noise also deliver power to a load? Which means, can I extract useful power out of noise? Mathematically, you have modeled as a voltage source. Noise has been represented by a voltage source. Yes, mathematically, from a circuit model point of view, you can extract power out of it. So that power, the available power that a voltage source of value Vn with a resistance Rs is, we just derived it, it is Vn square upon 4Rs. Now I'll take this in frequency domain and look at it. Vn square is nothing but the squared noise spectral density in frequency domain. I mean, these expressions are the same, and Vn square is the spectral density. That it is going to be 4 kT Rs divided by 4Rs. This term is kT. Now you should understand 4 kT Rs, the units is actually volt square per hertz, right? It's a spectral density. That divided by 4Rs is going to give me units in watts, because this is volt square and resistance in ohms. The units is going to be watt per hertz. So this term kT, it's called as the available noise power. So this is the power that a load resistance or a voltage or a noise source, the noise of a resistance can deliver to a matched load. Now this is not actually power; it is power per hertz. I mean, it's a spectral density. So I say an RF system operates around a carrier frequency with a bandwidth V. Now this is only positive bandwidth, but since we have only considered the one-sided spectral density, I can directly multiply the spectrum per hertz plot with the bandwidth. So this KTV is the power, the total available noise power. Okay, the units will be in watts. Now this equation tells us this is the power that a noise can deliver to a resistor with a noise can deliver to a matched load value or matched load of the value equal to R itself. Okay. Now this should sound counterintuitive because I mean doesn't make any intuitive sense because resistor noise, you can't derive useful power out of noise. It's a random thermal agitation of electrons. You can't extract any useful power. Then how did we derive this result? That comes from the mathematical model. We assume that noise as modeled as a voltage source in series resistance. So therefore, a voltage source, electrical from basic electric circuit theory, that can deliver power. But there is one other way of looking at it. Now, say I hold this resistor at a temperature R, or say Rs with a temperature T, and another resistance RL, which is also equal to Rs at T equal to 0 Kelvin. So which means this doesn't have any noise. But this guy is going to have noise. There will be random agitation of electrons. Now, because of the temperature difference, these electrons would now move towards the other resistor. But I'm going to keep this constantly at 0 Kelvin. So therefore, the electrons would keep on constantly moving in this direction. Okay. So that way you can see that this resistance is actually delivering power to this. Because in the previous derivation, I assumed that the other resistance RL is noiseless. So here, when I assume T equals 0 Kelvin, the resistance RL is noiseless. Okay. So the takeaway point or the main important point is the word called available noise power. It's more of an intuitive word. There is no real noise cannot deliver power to a load. It's more of an intuitive term, and that is KT. The units is watt per hertz. So if you know the bandwidth of the RF system, then multiply the bandwidth, you will get your available noise power in watts. You can also express this in dBm. Now this term KT, the value of this KT is minus 173.8 if you take 10 log of KT dB per hertz. It's also expressed in this way. Sometimes it's approximated to minus 174 for quick hand calculations. Okay, so this term is called the available noise power. So now we discussed two things. One is available power and available source power, or available power and available noise power. So for a voltage source with a finite source resistance, the available power is simply Vs square by 4Rs. And similarly, for a noise of resistance of value, any resistance, the available noise power is simply KT watt per hertz. KT is the available noise power. Now this value minus 173.8 or 174 is at T equal to 300 Kelvin. Okay, I'm sorry, I forgot to mention that. Okay. Now we will consider a general RF amplifier with two ports or four terminals with an input port and an output port. Now this has a finite input resistance, and I'll also see that it has an output resistance and a voltage gain. I'm going to call it AV, called the unloaded voltage gain, AV into Vin. Vin is the voltage across this. So the two-port model is going to be something like this. So Rn, so this is AV into Vin. Vin is the voltage across the resistance Rn, and Rout. Okay, so this is the two-port model for this amplifier. Now we will be connecting a source to the input of the amplifier with a source resistance Rs and a load to the output of the amplifier. Now Rn is the amplifier's input resistance, Rout is the amplifier's output resistance. AV, this term AV, it's called the unloaded voltage gain. So this is the voltage gain of the amplifier if Rs equal to 0 and RL equals infinity. Okay, So when you load the amplifier, we know that this call, let's call VL as the output load, output voltage. So VL by VS is the loaded voltage gain that we have already derived this. This is Rn by Rn plus Rs into AV into RL by RL plus Rout. So this is the loaded voltage gain, and this is always less than or equal to AV. Okay, and this is called the AV is called the unloaded voltage gain that happens when Rs equal to 0 and RL equal to infinity. And so this is the unloaded voltage gain. So now we'll get back to the amplifier. And let me also introduce one more term. So this term AV into Vin, I'm going to call it as V0. So this is the voltage at the amplifier output, not across the load, but just at the amplifier's output. So it is V0 is AV into Vin. So this term is the output of the amplifier. So now the two-port model of the amplifier. So I'm going to model it as this way. So I'm going to say that it has an input resistance, an output resistance, and an unloaded voltage gain. Now, if I connect a voltage source with a source resistance Rs, the maximum power or the available input power, I'm going to call it source power. PSAV is the available source power that can be delivered to this amplifier under matched conditions is going to be Vs square by 4Rs. So this is the maximum available power, source power at the source end. Now, similarly, I'm going to try and compute what will be the maximum available power at the amplifier's output. Okay, that depends upon the value of R out, because the amplifier can be equivalently, if I mod the Thevenin equivalent, R out will come as a Thevenin resistance. That is going to be V0 is the amplifier input, output at the V0 is the voltage at the amplifier's output. It's going to be V0 square by 4 R out. Okay, it depends on R out. This is the maximum power that the amplifier output can deliver. Now we know that V0, so this is your P out AV. And we know V0 is simply AV into Vin, which is nothing but AV into Rn by Rn plus Rs. Okay, so if I substitute this in this equation, I'll get the available output power is simply Rn by Rs the whole square into AV square, okay, into V. Okay, so that there is Vs here, I missed Vs, into Vs square. Okay, so this is your by 4R out. So this is your expression for the available output power. Now we know the available source power is Vs square by 4Rs. Now if I take the ratio of the available output power and the available source power or the input power, it's called the available power gain, GAVP. Okay, or I'll call it GPAV, the available power gain. This is the maximum power gain you can get out of an RF amplifier. Okay, and that will simply be Rn by Rn plus Rs the whole square into AV square into Rs by R out. Now, if you match the input port as well, when Rn equals Rs, if you have matched it, in that case, this result reduces to AV square by 4 into Rs by R out. Okay, or you can write it as Rn by R out. So this is your available power gain for matched input conditions. Okay, so available power gain is nothing but the ratio of the maximum available output power, or I shouldn't use the word maximum. Available power automatically implies it's the maximum available power divided by the available source power. That term will give me the ratio of the two will give me the available power gain. So we will be using this term, especially this term, when we analyze noise figure for cascaded circuits, for cascaded systems and RF receivers. Okay, I'll stop at this point. In the next lecture, I'll quickly discuss about noise figure and how do you figure out noise figure for cascaded systems.